This is a 3x5 card representation of the selection sort algorithm and its implementation. The selection sort is considered possibly the simplest of sorting algorithms. The card at the top represents a variable that will keep track of the smallest integer for each of our loop iterations. We'll call it POS for short, POS. The two cards below it, the cards labeled I and K, represent the counters for the outer and inner loops, I being the outer loop and K being the inner loop. K will always be set to I plus 1, so we'll always kind of see this arrangement of these three cards as each new loop starts. It's just that I will be incremented and all three cards will be moved over one space here. The row of cards with 0 through 6 on them represent the indexes 0 through 6 for an array. And for a zero-based index array, the bottom row of cards will represent the actual integers in the array. As you can see, they're in an unsorted. They're shown in an unsorted fashion here. Just kind of randomly set up these cards so that they're out of order, and we're going to go through the process of putting them in order with a selection sort. We'll start the sort with the outer loop at position 0 of the array, and the inner loop will always start at I plus 1, as I mentioned. So the inner loop being K, or the card with the K on it. The basic idea is to compare the value at the index pointed to by I with each of the remaining values to the right of it in the array, using K as the counter and keeping track of the smallest value for that particular iteration with POS. At the end of that iteration, a swap is performed between the values at the indexes pointed to by I and POS. And what happens if the value at I is the smallest to begin with? Well, after we iterate through the loop, if POS is still pointing to the same location as I guess in most implementations of this, you would still call the swap in a separate method, but the swap would just be swapping the values at those two positions, which it's really only one position. It's the position that POS and I are both pointing at. It's kind of a useless step at that point, but if that's the way the implementation is designed, and that's the way I'm going to explain it here, is that we're always calling a swap method at the end of each inner loop iteration. So with that, let's kind of walk through an example here. If we look at what we're going to do, compare the values at 0 or index 0 and the index 1, which is 2 and 5. Obviously 5 is not less than 2, so we're not going to move the position of smallest number. We're going to leave it where it is, but we will, however, increment K, and let's compare the value at index 2 that K is now pointing to, which is 1. Compare 1 to 2, or the value at index 0, and we find that 1 is in fact less. So we're going to move our marker over. Index 2 now contains the smallest number, and we increment K. So now we can compare K. We're not going to compare K to I. What we're going to do is compare K to the position that's marked as our smallest now, so which is now 1, and obviously K being 7, or pointing to the position that has a value of 7, that is not less than 1, so we're not going to move our position of smallest number marker yet, but we will increment K. 3 is not less than 1, 6 is not less than 1, 4 is not less than 1. So what we have to do now is perform a swap between POS, or the position pointed to, marked by POS, with the position pointed to or marked by I. So 1 or 2 and 1 are going to be swapped down here. And we'll see that in the next frame. And we increment or then increment our outer counter I. And as I said before, we're always going to start pause at the position, the same position as the outer loop. We're always going to assume that that first position of the outer loop, excuse me, that the outer loop is pointing to, or starting from, will contain the smallest number until we find something less to the right, or unless we find something less. So now we're going to compare the values. K also is I plus 1. We always set that to I plus 1. So we're going to compare the values 2 to 5. 2 is less than 5, so we'll actually, in the next frame, we'll move the marker over for position of smallest number and increment K. So now we're going to compare the value at K to the value that pos is pointing to, which is 2, and K is not, or that value at K, which is 7, is not less. So we'll increment K. 3 is not less than 2, 6 is not less than 2, 4 is not less than 2. So now we can perform a swap between I and pos, or the values that those two variables are pointing to. So 2 is going to swap for 5, and now we have the numbers 1 and 2, or the integer values 1 and 2 in order in our array. We start the process over again. I increments to the value of 2 to point to the index of 2. And of course, pos is going to reset to wherever I is starting off at. And K is I plus 1. So we compare 7, the value of 7 to 5. It is not less than, so we increment K. 3, in fact, is less than 5. So in the next frame, we're going to see we move pos over. 3 is now our current smallest number in this loop iteration. K is now incremented to index 5, which is 6. 6 is not less than 3. 4 is not less than 3. So now the swap is going to be performed between pos, or that number that pos is pointing to, which is a value of 3. We're going to swap 3 with 5 here, where I is pointing. And now we have the first 3 numbers in order in the array. The next one here, we increment I, reset pos to where I is, and the value of 7 is now assumed to be our smallest until we find something else. K is I plus 1. The value of 5 is in fact less than 7, so we're going to mark that as our new smallest number. Increment K, but 6 is not less than 5, so we'll leave pos where it is. Increment K again. 4 is in fact less than 5. So with that, we are going to mark that as our smallest number. We're at the end of this inner loop iteration. We're going to swap pos with I, or the values that those are pointing to. 4 gets swapped with 7. We now have 1, 2, 3, 4, 5, and the rest of the array just happens to be in order, so there's no need to go any further. The loop, or the algorithm, would still go through the remaining loops. We just won't show it in the frames here, but the process would continue. In fact, what we would find is the situation I mentioned before, where for the final loop iterations, pos would be pointing to the same value as I, and if you're calling a separate swap method, the method would still be called. It would just be called with the same values. Kind of a wasted step, but the selection sort is not necessarily, not by any means the most efficient sorting method, but nevertheless has its purposes to study and understand how it works. And if we kind of loop through this kind of quick here, this looks like a stop animation thing, stop time animation thing. There we go. Thanks for watching. This is a selection sort example.